Welcome friends, I am Tanmay. Welcome you all in my channel Chemistry, the Mystery of Molecules. So today we will discuss a basic reaction, that is halogenation of alkene. Mainly we will discuss about bromination of alkene because that's the most important part of this reaction. And today's lecture will cover few points. For example, basic concept for this reaction. Second is the mechanism associated with this process. Then we will discuss the comparison between the reactivity of chlorine versus bromine. As we told that bromination means, then definitely question what is the chlorine, because it is the cheapest one compared to bromine. So this comparison between chlorine and bromine's reactivity, then make proof of this mechanism, and after that this reaction could be a tool for the protection and deprotection of double bond. We will examine and finally we will give some example to complete this discussion. Okay, so let's start. Now as you can see, this is a double bond, means it's a single sigma bond, it's a sigma as well as sigma bond as well as a pi bond. This double bond is made of this part. Okay, so it reacts with bromine and chlorine to produce this. How this reacts? Because if we consider this halogen, this halogen should be presented as, instead of Br2, we can present this as a Br. Okay, and we know that such halogen molecules can act as a Lewis acid also, because that energetically accessible vacant orbitals. Okay, so it can. So what can happen? This double bond can go and attack bromide and it can leave, and in this way reaction proceeds. So to understand the overall process, we need to understand the mechanism properly, then you can understand mechanism. Okay, so when it attacks, it produces, this is a double bond. These are, you can consider, 4 substituents of this double bond. So this, and see, this double bond attacked bromine, and actually the pi bond attacked bromine. Okay, the pi bond attacked the bromine. So expected that we can think in this way, this Br2, just a complex Lewis acid base complex. Okay, which is Lewis acid? This is Lewis acid, and Br is a this is Lewis base and Br is a Lewis acid. Fine. Okay. So after that there is this reaction. For example, these will attack Br and will leave. So what it produce? So this produce ultimately, this is a double bond. This. So as we told that will attack, means it is expected that both double bond is interacting with the bromine. So we can consider the transition state like this. This is the bromine and this is, since this bond is broken. Okay, so here, so this is the thing. Now what happens, that one bond breaks, it leaves. You may think, I am not saying that every step, I am saying this because it will help you to understand this phenomena properly. So what happens after this? So it will result, this is a bromine, this is a cation, and one bromonium ion is outside left. Now you can think that this will attack and produce the product, and keep it in mind, if it is carbocation, means that is a 6 electron species and sp2 hybridized, and there is a vacant p orbital. So we can, this bromide can attack from this side as well as this side, but actually that doesn't happen. We get always anti-product, means this is anti-product or anti-addition. Okay, so this means reaction is not happening in this way. What actually happens, that this bromide have 3 lone pair, so it attacks this and it produces this bridged bromonium ion. This is, and since it produces, it is a plus charge, So now actually if this step is not produced, what happens? Directly from one step it produces this bridged bromonium cation. So now we have observed that bridged bromonium cation is obtained as a product. Now what can happen? There is another Br minus. So this Br minus can attack this carbon, for example path A, or you can think like that it can attack this carbon, that is path B. So whatever this attack, it will result ultimately an anti-addition. Means, for example, let's consider the one, both are same. So if this attack, it will open up. So this here will be the Br and here will be the Br. So in this way the reaction proceeds. Okay. Now the question, as I told, basic concept I have covered. Now mechanism I have told. Then comparison between chlorine and bromine, and that is the interesting part. Why this bromine, these three member ring, these three member ring forms easily. Question, why this forms? Because first of all, one, larger size of bromine atom. Because if it is larger, then strain factor will be less. Let me give you a clear idea. Let's think just, this is the atom. So right now in this way, this is not oxygen. For example, this is a something else. Now you can consider some atom X. So if this is bigger relatively, this much. Now see, this is, and for example this is x1. Now this angle, this x1 is greater than x. So if it is, then the angle strain is less, and exactly that is happening in case of bromine. Okay, so that is the reason this bigger size of bromine helps in this formation. First point. Second is that bromine, means if you compare chlorine versus bromine, bromine is to moderately, you can say moderately electronegative compared to, why I am writing this, compared to chlorine, because bromine is electronegative atom, but if we compare with chlorine, this is relatively less electronegative. So now consider that this chlorine reaction happens. In a similar fashion, this reaction will happen, and what it will produce? It will produce bridged bromonium ion. Okay, as this is bromonium ion, Bri, bridged bromonium ion, or you can say cation. So this is chloronium ion. Fine. So if this chloronium ions from now, the size of chlorine is less, so more strain, first factor. Second, it is more electronegative. That's why it will not like to have positive charge. Consequently, what can happen? It can withdraw. So here the chlorine, here the positive charge. That is, so this is possible, and that is the reason in bridged bromonium ion case anti-addition is product, and in this case mix is produced. Mixed means one is anti, definitely, but along with this anti product there is some, means it is opened, some amount of carbocation form. So let's say p orbital. So both side of this is a p orbital. So both side of this p orbital could be attacked by the another chloride anion present in the system. Okay, so both sides possible. So that's why mixture of product is obtained, and that is observed in reality. So this is the reactivity of this bromonium ion. But as I told that this comparison we have discussed, fine. Now is a proof of concept. So we have understood why chloronium, and another thing, chlorine, keep it in mind, is a gas, so difficult to handle, whereas bromine is liquid, so you can handle it properly. Fine. And since this chlorine is gas, and another thing, more electronegative, more reactive, so difficult to handle. And another thing, it is relatively less functional group tolerant, means when it affects other functional group more compared to the bromine. So that's why when we have a chance for bromination versus chlorination, we will prefer bromination. Fine. And another thing, keep it in mind, this is a reaction where bromine is reacting with the alkene and produces this, and this is actually colorless. This is colorless, this 1,2-dibromo compound, and this bromine is red color. This bromine is red color. So that's why in this way, this is a tool for the detection of double bond, and there is a difference between aliphatic double bond versus aromatic. Then that is a detection test. I'll explain that in details in the next video. So whatever, this is a reaction. Fine. This is a detection tool or technique for double bond, that is decoloration of the red color of bromine, which proves the presence of this alkene type double bond. Okay, fine. So now we have discussed about this. Let's go to some proof which will support this process. Now you can see the proof of this bromonium ion addition. Okay, why, as I told, bridged bromonium ion formed, that is. So now you can see this is, you can say, cis butene, or you can say Z butene, whatever you want. It's a two nomenclature. So if it reacts, it will produce bromonium ion. What do I mean? That this double bond with this bromonium ion, this methyl, this is the methyl. Fine. Now another bromine, another means these are hydrogen. I am not focusing. So this bromine can attack this center or can attack this center or this center, whatever. So based on that, two product will produce this and this. So this is the reason, and they are optically active. Okay, so they are optically active, but and because of this two position attack. But if you take the corresponding trans one, what do I mean? Means this one, methyl is, one is here, one is here. This is hydrogen, this is. Then the product will be obtained is, I am just changing this. Methyl one is here, just one position change. How? Why? Because see, the one part, this part is changed. Means from methyl came to here, this. So actually this part will change. So this is actually a meso variety. Meso variety or meso variety, whatever you say. So this way, indirectly proves that this reaction happens to bridged bromonium ion. Otherwise, it is not possible to get two particular product. In one case optically active mixture, that is a racemic mixture, and another one case optically inactive, that is a meso variety, because of this. Okay, so this is a proof number 1, and this is a proof number 2. Here you can see this is adamantane derivative. Okay, it's a double bond. This is the double bond attached to this adamantane ring. So this is the double bond. So it reacts with this bromine, similar fashion, and what it produces. So first step is that, okay, this will attack this thing, and it will leave. Fine. This bromonium ion and bromide ion both are produced. This is the bromonium ion 3-member ring, but this ion pair is isolated. You may ask why this is isolated? Because you can see this portion, there is a H, there is a H, and it's a completely locked system. Completely locked system. So the bromide anion cannot attack. The bromide anion cannot attack. That's why this ion pair is isolated. So this is the most interesting proof of this concept, that this reaction proceeds through the 3-member ring formation. Okay? Okay. Here you can see that we need a particular oxidation. Okay? This aldehyde is needed to oxidize into carboxylic acid. So the question is how we can achieve it. If we use normal oxidizing agent, for example, anything like we can think that if we use nitric acid, means easily available oxidizing agent, then it is expected that this aldehyde will be oxidized to corresponding acid. But there is a problem, that this unexpected oxidation of this double bond, which is a problematic, and if it has happened, then there may be variety of chances. How to avoid this issue? This issue could be avoided first, the protection of this double bond, reaction of this double bond. What we can do? We can do using bromine, for a solvent could be non-polar solvent like carbon tetrachloride. So what will be the product? We know that it will be a anti-addition product. Fine. So this one is bromine. You can think that here it is up, it is down, doesn't matter. Actually, this is optically active variety, as I explained in the previous example. So both are possible. So this is, now if we do the nitric acid oxidation, means this one. If we, sorry, I made mistake. So now if we do the nitric acid oxidation, using nitric acid if we oxidize, then this aldehyde group will be converted into this corresponding carboxylic acid. Fine, this is Br, this is Br. Now if we put zinc dust in methanol or sodium iodide in acetone or potassium iodide, so then it will result the final. Means this 2 bromo will be eliminated, dibromo elimination to produce the double bond. Now the question, how this step is happening? Means this sodium iodide or zinc, how this step is happening? This is happening, for example, if we consider the sodium iodide version, iodide can attack any of this. For example, this I minus can attack here. It is logical that attack will be here because it is relatively electron deficient, and the produced this, if it attack, there is a charge density enhancement on this carbon, so expected this will be the better chance. You can draw the other one also, but based on my understanding it is more logical. So it will attack here, and this way bromine will leave. Okay, so in this way this double bond is forming. Okay, fine. So this is the thing. But in case of this zinc, how this reaction is happening? RCH, Br. Similar thing you can think, that zinc is capable to produce 2 electrons. Zinc can give 2 electrons plus zinc plus. Actually reaction in this way, you may write the reaction that zinc lone pair, that is attacking, this is coming and this is eliminating. You may draw, but I believe more logical is that instead of zinc, you can write this that 2 electron actually attacking. 2 electron is attacking this, and what is produced? This final product as well as zinc bromide. In previous case, what was it produces? The sodium iodide thing, that it was producing IBr, because iodide attack to Br and plus Br minus. Fine. So this, and interestingly, if we add iodide in this solution, for example, means is excess iodide is there, so that can react with this and it will leave. So what will be the product? That will be iodine plus 2 Br minus. So that is the reaction. So in this way, this is the strategy. This is the strategy for the protection of double bond. And another thing, this means this is the strategy for this protection of double bond, and protection as well as deprotection, and using this strategy we can oxidize the particular group, for example this aldehyde to this corresponding acid. So this is the interesting part of this strategy. Okay, so now let's discuss some examples regarding this reaction. Okay, so let's discuss some examples. Okay. So in the first example, you can see there is a reaction between this double bond, bromine carbon tetrachloride produces an HBr. Since bromine is reacted and HBr produces, we can estimate that there is a double bond. This means first is addition, then means elimination. That type of reaction happens. Second, there is a double bond formation. Why? Means single bond formation. So in this way, it is very important to use double bond equivalent or DBE. So right now if you consider this double bond equivalent theory, double bond equivalent. So if you consider this double bond equivalent method, then see that actually this is a substitution reaction. This is not an addition reaction because one double bond consumed from here, but one ring means bond is formed. So that's why this is produced. So it is like an addition, or you can say elimination. Both are happening. So question, how this is happening? So if you recall the previous part of this discussion, where I clearly described that what happens in the first stage, there is a bromine addition in this double bond. So what it produces? It produces bridged bromonium ion. This is the bromine, bridged bromonium ion, and along with that bromide minus is there after reaction with bromine in terms of non-polar solvent like carbon tetrachloride. So now here this NH can attack any position. For example, these and this, because this is symmetrical, and if you consider the numbering 1, 2, 3, 4, 5. So if it attack, there will be a 5-member ring, and if it is 5, then it is 6. So 5 and 6-member ring. So this is, it will attack, and ultimately it will result this, because it will attack and this will open. After that, this nitrogen have a positive charge on it and it will release the proton. Previously there was a bromide anion, now one proton released, so these will mix together to produce this HBr. Now the question, how you can understand this reaction will happen? What is the thing? Actually all these carbons are sp3 hybridized. So if you think properly that this is sp3, this is sp3, all are sp3. No double bond is there right now. So if it is sp3, the advantage is that angle is 109 degree, not at 109 degree 28 minutes, but not 120 degree, because in plane it seems like 120 degree, but actually the reality is not 3D. So what happened? These and after this, what will happen? This NH is not at this place. It is closer to this double bond in this fashion. You can say if the double bond is here, NH is in this, so it can easily go. So don't consider the distance is too long. Actually, distance is too short to form the bond. That's why this. And second, intramolecular reactions are always preferred over intermolecular reaction. Keep this statement is mine. Intra is preferred compared to intermolecular one. Keep this statement in mind, because means the simplest example. You want to hit someone. What you can do? You can go and hit. There is a chance that that person may escape from there. Compared to that, if you hold one hand of that person and hit, you can definitely hit. Hitting a person and this hitting, that is an intramolecular one. And the person I am not holding, there I am going to hit, that is an intermolecular one. And reaction is nothing but based on two things. One, collision theory, one, transition state theory. I will explain these things details in future. So first collision, then transition state. So in order to have a proper collision, if we hold it, the probability of effective collision increases, the chance of reaction to proceed is increases. So in this way, this reaction happens. So this bridged bromonium ion formation followed by the opening of this NH by neighboring group participation. Neighboring group participation. So this is the example of bromination with neighboring group participation, which ultimately results in this. And another thing, if nitrogen attacks, the next carbon will have bromine. So this is, and this is the HBr. So in this way, this reaction proceeds. So this is a very good example. I suggest you that, I guess you have understood this. It is very helpful for the clear of this basic concept. Okay, fine. Now let's go to the next example. Next example means this is a bridged bromonium cation, as we have discussed previously. If we react this bridged bromonium in presence of methanol, because methanol is excess compared to this, so that's why methanol can attack. Means I am saying that it will come, it will attack, can here attack, can here. So ultimately what will be the product? So this is the 4. Okay, let's consider it is attacking in this way. Both are same. right now. Since I have not provided any substituents, so effect of those substituents is negligible at this condition. So here will be OMeH plus this, and second step, this OMe will leave this proton. So what will be this, and since one proton is coming from this side H plus, and another thing there is one Br minus, so it will produce HBr. Fine. So this is like a ether formation. This is the halo ether formation. This is the halo means bromo, and this is the methyl ether. Okay, fine. Similarly, if we take acid in terms of dilute acid and water, if we produce, so what will be that? It can attack both sides. Let's consider this. So what will be the product? This is the bromine. This is the OH H plus, similar like this. So again it will this eliminate this proton, and what will be the product? This is the HBr. Now please keep one factor in mind. When we write H plus, this means the counter anion is non-nucleophilic. Okay, non-nucleophilic. What does it mean? For example, you can consider sulfuric acid. What it produces? It produces H plus, 2H plus plus SO4 2 minus. This is non-nucleophilic. So in this way, actually when we mention this, but if there is a nucleophilic counter anion in relatively higher amount, then there may be a competition between the nucleophilic atom of water versus that the halide means, not halide, means corresponding anion. For example, if you consider HCl, and it is in large amount, so there will be a competition between chloride versus water. So it depends. So when there is nothing mentioned, you consider that the effect from the counter anion will not be there, it's negligible. Only this part will act as the nucleophile for this reaction. Okay, fine. So we have understand this formation, and this you keep it in mind, this is called halohydrine. Okay, so this is halohydrine, means halogen and alcohol. This is called halohydrine, or you can say alpha halohydrine, better to say. Now you can see this same reaction here, double bond is there, along with that silver acetate is there. That is the interesting part. So this double bond and bromine, it will react to produce, as we know that react and produce this Bridged Bromonium cation. Fine, very good. This is Br plus and this is Br minus, and we know that silver plus has a very good affinity for this, so they will react and produce silver bromide, and that is insoluble, so precipitate. Insoluble silver bromide will come out from the reaction. Now just think, previously there was an nucleophilic counter anion, that is bromide. It is eliminated. So what is present in the medium? That is acetate. Because how many bromide is consumed by this silver, that many acetate will be there, because EgOSC single one silver is to one acetate. So right now the nucleophilic bromine is not present in the medium, so that's why acetate will act as a nucleophile. So it can attack here or it can attack here, both equal probability, since I haven't given any substitution. So but when there is a proper substituent, you have to think their effect and decide what will be the product. For the simplicity of understanding, I haven't mentioned that. So fine, if it attacks, what will be the product? It will be one part is bromine final, and another thing, if it attacks, it will open, because bromine has a positive charge, so it will neutralize the charge. So this is, and this is acetate, OCO, COCH3, fine. So previously we had seen there is a OH or OMe, right now this is OSC. So if we hydrolyze this OSC, this will be converted to this alcohol, this, and this is called halohydrine. Okay. And here instead of halo we will write bromohydrine, because the halogen is the bromine. Okay, so 1 2 this difunctionalize this thing, and this is a very important material, as if you put base on this, for example, means if you put any alkali, what it will produce? It will come and abstract this OH, so it will be O minus. This O minus will attack here and it will leave, and it will ultimately produce epoxide. Okay, so this is one of the very important example of halohydrin. I will explain in a dedicated video about halohydrin in future, so you will have complete understanding. Fine. So this we have discussed. So now the question is about NBST. So for this example, I want to mention you that we have previously explained about the bromine addition using simple molecular bromine, and we know that actually the nucleophilic attack is happening on this bromine to produce this bromonium cation as well as the counter anion. Now question, if we can provide bromine cation directly, means I am saying that is it possible to provide this bromine plus? Actually this is possible. Why? Because we know that bromine is electronegative atom, fine. So it is expected that bromine will always prefer to remain in minus state. If we consider this bromine, this is actually neutral, or we can say little polar. In this way, this will be little plus, this will be delta minus, but nothing else. If we say HBr, then this is delta minus. So not, but and why this is delta minus? Because this is less electronegative. That's why this is delta plus. But consider if we add some more electronegative atom compared to bromine, then there is a chance that this bromine will be plus. Fine, that is the thing. And one actual reagent at this situation is N-bromosuccinamide. Okay, so keep it in mind. This is the background concept of choosing such reagent. Okay, this is the N-bromosuccinamide. What does it look? So we know succinic acid, it's a 4-carbon acid. So this is the succinic acid derivative, and actually this is succinic anhydride. Okay, this is succinic anhydride. This is succinamide, means this is succinamide. Fine. And I told N-bromo means nitrogen will be attached to bromine. So this is N-bromo, and we know that nitrogen is more electronegative compared to bromine. That's why in this case bromine is delta plus, nitrogen is delta minus. Second, for example, if somebody attacks on this bromide, so what will be the product? It will produce, this bromine will go, and if it attacks some nucleophilic attack on bromine, then this bond will come on nitrogen, means the lone pair will come on nitrogen. So this is the minus, this is double bond. So what happens? So this nitrogen, this is an anion, means the negative charge on nitrogen, and that is stabilized by resonance using this. So we can draw the canonical structure. This is a double bond. So sorry, this should not be double bond. Succinamide. So this is O minus. This is double bond N. This is similarly. This could be stabilized by this another one. So in this way, this is stabilized. So means it's a completely designed substance for this purpose. So fine. So what happens in this way? If this double bond goes and attacks this bromine, it will come, and whatever. This will result in this Bridged Bromonium Ion formation, bromonium plus, and along with that counter anion will be this one. Understood? This anion. So no, let's consider this as a minus. So this is A minus. Fine, stabilized through resonance, doubly stabilized, not only stabilized, it's doubly stabilized. So fine, then and this thing is done in presence of acetic acid medium. So what does happen? This A minus is relatively stable, so this will not attack as a nucleophile. Compared to that, what can attack as a nucleophile? This acetic acid, because acetic acid is CH3COOH, and we know that this lone pair pushes and this can attack as a nucleophile. So it will attack both sides equal probable, just I am showing here. So if it attacks here, it will be open up this side. So here already 4 bonds, so this bond will open up. So ultimately what will result? Maybe I have done mistake in the previous thing. Always keep it in mind. opening up will be here. Wherever this attack will occur, opening up will be happen from that carbon, because it is already 4 valency, but it opened up. So it result in, maybe I have done mistake in the previous example. So please don't understand the wrong. I'm sorry for that. So this is here it is attacking. So this is now bromine attached, and here OAC. There is a proton. After attacking, this proton will be eliminated. Second step. Fine. This is, and like the previous example, in presence of acid H3O plus, it will ultimately result this halohydride, bromohydride via OH. So this is the overall discussion about these examples. So what we have learned today? We have learned about the basic concept of bromine addition to the double bond mechanism and the comparison with chlorine. Why? Which is more important, chlorine addition or bromine addition? What is the difference? And reactivity. Say in the subsequent stage, we have discussed about the proof of this mechanism. That is the means isolation of the bromonium cation using adamantane double bond. So double bond in between two adamantane ring. So that is fine. After that, we have discussed about the bromination and debromination. As what do I mean? Bromination is a protection tool for protection of double bond for chemical conversion and further recovery of double bond using sodium iodide or zinc metal. And finally, we have discussed few examples which shows that this bromination using NBS, that is a bromine cation, means cationic bromine species, and other reagents, and preparation of halohydrins, or more specifically if we say bromohydrins, it's a very important substance. So this is the complete discussion of this topic. If you like my teaching, please help me in my channel to grow. Why? First of all, you subscribe my channel Chemistry and History of Molecule, and please like my videos and share these videos among your friends such that many people could be benefited from my effort. And finally, please press the bell icon to get the notification of every single video I upload. So see you in my next video. Till now, stay happy, stay cool, and stay blessed. All the best.